FET circuit, there are three parameters. Okay, so one is the gate voltage VGS, another one is the drain voltage VDS, and the drain current ID. So we have three varying parameters for FET: VDS, VGS, and ID. So how to select the proper operating point for proper amplification? So that is all about FET biasing. That means how to select the actual value of ID, the actual value of VDS or VGS, okay, using that analysis. So that is basically the biasing of FET. And when we discuss the FET chapter, the JFET and MOSFET, etc., for JFET, you know that the current equation ID, that is something like this: IDSS into, okay, 1 minus VGS by VT square. We are already familiar with this type of equation. So that is the current equation for JFET. Similarly, MOSFET also, there are some other type of equation, but we are not going to discuss that part. So talking about biasing circuit, we have a fixed bias similar to BJT. The concept of fixed bias is we are using only a single resistance to provide the biasing. That means if I draw the circuit, okay, the circuit will be like this. Let here let this point is grounded, and this resistance RG, and here we are applying some voltage VG, and here we are applying some input, that is the source signal Vin, and this one is the supply voltage VDD, and you can take it one resistance RD, and we are taking output voltage from here, V0. Okay. So this biasing circuit is fixed bias circuit, where the biasing is done by using this resistance RG and this voltage VG. So it is same as your BJT fixed bias. So just try to remember, for BJT fixed bias circuit, it was something like this. The biasing resistance was connected to this VCC. Okay. So similarly here, the resistance RG is connected to some separate voltage source VG. Okay. So by using that, we can get a particular value of VGS by depending upon the value of this VG. We can set a particular value of VGS, and as a result, we can control ID, and also depending upon the value of ID, we can select what will be the value of VDS. Okay. So basically, biasing means the selection of all those parameters which is required for proper amplification of signal. Similarly, similar to your BJT amplifier circuit, we have a self bias, which is another one popular biasing scheme for BJT. The same thing we can do here, self bias circuit. Okay. And you know the architecture of self bias. So that is, here we have one resistance RT, and here we have RS. And this side, you know, two resistance voltage divider network will be formed, R1 and R2. This is grounded, and this one is plus VDD. So this is R1, this one is R2, and we are applying signal here for amplification. It is exactly same as your BJT circuit, only the BJT is replaced by FET. Okay. This, and here we have a capacitor, you know, that is for amplifier design, okay, to improve the frequency response. And we are taking output from here, self bias. So self bias, you know, the voltage divider bias. Again, here you can say that the voltage drop across this resistance RS, the source resistance RS, it will provide a negative feedback. Similar to BJT, the voltage drop across emitter resistance will provide a negative feedback. Okay. So we have a fixed bias circuit for FET, we have a self bias circuit for FET. So depending upon the requirement, so you can apply a suitable biasing circuit for it. So this is basically the basic idea about the FET biasing. And to calculate any parameter, you can take help of this equation, and also you can apply KVL at the output side if you are interested to find out what is the value of VDS, okay, for a given value of ID and all those things. So the input side equation is this one, ID equal to IDS is into this, and output side equation, you can apply KVL at the output side. So with the help of those equations, you can calculate the required parameter. Suppose for a given value of VGS, you need to calculate what will be the value of ID and VDS. So with the help of this equation and output side KVL, you can calculate that. So now coming to the small signal model and FET amplifier analysis. So for BJT, we have a model that is the hybrid model. Okay. So we establish hybrid model just for the small signal analysis. Okay. So we have complete hybrid model, original hybrid model, we have simplified hybrid model, etc. But for FET, there is no such hybrid model. Okay. So for FET, we are going to establish one model. So that will be used to analyze that FET amplifier. Okay. So what will be the value of gain? What will be the value of impedance, etc. by using this FET small signal model. So compared to BJT hybrid model, that is H model. So if you check, it looks very simple. The FET models are very simple, especially at low frequency. And yeah, another one thing, here we consider that we are working in the low frequency region. That means the effect of parasitic capacitances are not considered. Okay. When we are working with the low frequencies, there is a late audio frequency range, the effect of internal capacitances, device capacitances, whatever the parasitic capacitances are present, we are not going to consider their effect. Okay. So first, let us establish the FET small signal model. So FET small signal model at low frequency. Let us see. In case of FET, so the terminal voltages for FET, that is basically the drain voltage and gate voltage with respect to source. Okay. So what I'm saying that the drain current for FET, that may be a JFET, maybe a MOSFET, the drain current of FET, it is a function of the value of gate source voltage, the value of drain source voltage. The drain current of FET is a function of gate source voltage as well as drain source voltage. So we are working with the small signal model, so that's why I have written all the parameters in small. ID is a function of VGS and VDS, where ID is the drain current, VGS is the gate to source voltage, the varying component, and VDS is the drain to source voltage. Okay. So whenever any one of those parameters will change, there will be some variation in the drain current. Okay. If VGS changes, keeping VDS constant, so of course ID will vary, or when the drain source voltage changes by keeping VGS constant. Okay. So this is the relation. So, and you know that the small signal models are generally formed by using the linear circuit element. So again, go back to our previous assumption. We assume that the signal variation with respect to the operating point is small enough so that the characteristics of the device can be represented by using some linear circuit elements such as dependent sources, resistors, etc. So that is the basic fundamental assumption behind the establishment of small signal models. So here also we are doing the same. So how to represent this function? So basically ID is a function of VGS, so that can be represented in this form GM-VGS. So the dependency of ID, okay, means how that ID depends upon VGS. So that basically depends upon the value of GM. Okay, so ID equal to GM-VGS plus this dependency on VDS. So that is basically GD into VDS or GDS into VDS. Okay, so how this ID depends upon VGS, that is represented by this factor GM into VGS, and how ID depends upon the output side voltage VDS, that depends upon GDS. Okay, so this term GM is called the transconductance. Okay, so that is here. In this case, it is ID by VGS when VDS equal to 0. So actually, in derivative form, GM equal to, okay, del ID by del VGS, okay, when VDS equal to constant in derivative form. The GM is called the transconductance del ID by del VGS when VDS equal to constant. Okay. Similarly, can you tell me what will be the definition for GDS? GDS that is equal to ID by VDS when VGS equal to 0, or in derivative form, it is del ID by del VDS when VGS equal to constant. Okay. So this GDS term, it is called output conductance or drain conductance. Okay, it is called output conductance or drain conductance. Also, we can write GDS equal to 1 by RD or 1 by RDS, because G stands for conductance, R stands for resistance, so it is 1 by resistance, where RD is the output resistance or drain resistance. So if GDS value equal to del ID by del VDS, so of course we can say RD will be just opposite of that, that is del VDS by del ID. Okay, so if I write in a new page the relation, the different factors, so GM, so that is basically in derivative form, is del ID by del VGS. Okay, and GDS, that is del ID by del VDS. So RD or RDS, that is equal to del VDS by del ID. Okay, so those are different constants. GM is called transconductance. So why it is called transconductance? The reason is clear. Check the output current, that is ID, controlled by input side voltage, that is VGS, so that the conductance looks transferable. The effect of input voltage, that is gate to source voltage, is being transferred to the output side. And GDS, both are output side parameter. ID is the output current, VDS is the output voltage. So that's why it is called output conductance. And this one is called output resistance. Okay. So rewriting this equation, ID equal to this one, so we can write, just putting GDS equal to 1 by RD, so we can write it ID equal to GM VGS plus GDS into VDS. GDS means 1 by RD, that is VDS by RD. Okay, so both equations are correct, so you can use any one. Okay, so this is the IV relationship, okay, in case of small signal model. And we can introduce another one parameter, that is amplification factor, that is called mu. So mu equal to actually, okay, so we can write in derivative form del VDS by del VGS. Means when we are changing the input voltage, how the output voltage changes, that is called gain or amplification. Okay, so that parameter we can write del VDS by del ID into del ID by del VGS. So we can write it in this chain by using this chain rule. What is the first term? This term? Which one? What is this?
RD.
RD. So mu equal to RD into second term, del ID by del VGS.
GM.
It is a relation between this mu RD and GM, the amplification factor mu, that is equal to RD, the drain resistance or output resistance into the mass conductance. So this is an important relation in case of FET devices. So mu equal to RD into GM. Okay. Now let us establish the circuit. So we have already already established that equation. So what about circuit? So FET small signal model, again I am telling at low frequency. So we are not considering the internal capacitances. Okay. So let us see. So first we have a 3-terminal, draw them. This side we have the gate terminal of FET, this side we have the drain terminal, this side we have the source terminal. So you can see it is similar to your base emitter and collector of FET. Okay. And in case of FET, you know it is having very high input impedance. That is the gate and source. The input impedance is equivalent resistance connected at the input side that is very high. So the resistance between gate and source is very high. So we can consider it is open circuit. Okay, because the FET devices, whether it is JFET or MOSFET, it is having very high input impedance. So we consider the gate and source is open, because you know when one impedance value is very high, so we can consider it as an open circuit. And the voltage we are applying between gate and source is VGS. And the voltage at the output side, that is VDS, in between drain and source. Okay, and this current is what? ID. Okay, this current, the current flowing at the drain terminal is ID. Now check, ID having two parts. Here, this is part 1, this is part 2. Okay, so the first part of ID, that is GM into VGS. Okay, so this is ID1, GM into VGS. So how to implement that? The first part in GM VGS. Okay. And the second part of ID, check VDS by RD. Okay. The second part of ID, check the second part is VDS by RD. Now check, we have VDS here. We have the output side voltage here. So if I draw one resistance here, RD, so what will be the current flowing to this resistance? See, total ID divided into two parts. First part is GM VGS. We have already satisfied this one. And second part, it should be VDS by RD. Now consider the resistance of value RD. And the voltage across this resistance is VDS. So what will be the current flowing through? So since this circuit satisfies this model, this equation, so it is the small signal model, low frequency small signal model. Okay, just very simple. So there is no such HI, HR, HF, and HO. Okay, the input side, the gate and source, it is open circuit, and the voltage you are applying VGS, and the output side, so there is a current source GM into VGS. Okay, there is a current source GM VGS, and there is a resistance RD, and you know what is GM, what is VGS, and what is RD, etc. So this is the small signal model of FET at low frequency. And high frequencies and extra capacitances will be connected. We are not going for that analysis, but if anyone interested, so you can check in between gate and source, some capacitance will come here. In between gate and drain, here one capacitance will come, etc. at high frequency. So now this model will be used similar to your hybrid model. This model will be used to analyze the FET. Now, what are the different types of FET operating modes? You know, for BJT we have common emitter mode, we have common base mode, and common collector mode. But for FET, it is a 3-terminal device. So the terminals are source, gate, and drain. The 3-terminal device. So we may here we can represent. We may say that the different modes of FET that may be common source, just following the BJT, will be common gate, because it is a 3-terminal device similar to BJT. We can say there may be 3 possible operating mode. So similar to your BJT, that is common emitter, common base, and common collector. So here it will be common source, common gate, and common drain. Okay. But out of 3 modes, this common gate mode having very less application. In few cases, in few special cases, this common gate mode is used. It exists. It is not like that there is no such common gate mode. It exists, but the application is limited. Okay. So the common source and common drain mode is widely used, mainly common source, because the common source similar to your common emitter mode for BJT, and common drain similar to the common collector mode of BJT. Okay. So we will discuss two different type of amplifier. One is common source amplifier, and second one is common drain amplifier. Okay. So we are not going for the analysis of common gate amplifier. We will discuss common source amplifier and common drain amplifier. Okay. This. And what are the parameters we are going to study? That is voltage gain, only two parameters, and output resistance. Okay, we are going to study two parameters, voltage gain and output resistance. So why we are not going for a current gain? Because you see the FET devices, the input side impedance is very high, input impedance is high. So if you want to calculate current gain, that is output side current by input side current, so basically since the input side current tends to 0, so it's not required to calculate the current gain. Okay, instead of current gain, we are interested to find out what is the voltage gain and what is the output resistance. And you know the input resistance calculation also not required because by default the FET devices having very high input impedance. So no need to calculate it separately. Okay, so we are going for a voltage gain calculation and output resistance calculation for common source amplifier and common drain amplifier. So let us see how to calculate that. So with source amplifier. So common source amplifier exactly same as your common emitter. Okay. So source is grounded. Okay. So here you have some load resistance VDD. You are taking output from here V0, and input side let you are applying some voltage VI. A very simple circuit I'm drawing. Okay. So this is the common source amplifier, the basic common source amplifier. Okay. So if I mark the terminals, this is drain, this is the gate, and this is the source terminal. Okay. So the next thing is we have to represent this using a small signal model. Okay. So small signal equivalent circuit. Small signal equivalent. So how to draw the small signal equivalent circuit? The process is exactly same. Previously you had but each model of BJT. Now you have to use this model, this small signal model. Okay. Rest of the part is same. That means here first draw the model. Okay. So this is the gate terminal, this is the source terminal, and this is the drain terminal. Just follow. And the gate terminal, what we are applying? VI. We are applying VI. Okay. And source is grounded, so we can put ground here, and this one is also grounded. Fine. The voltage between gate and source, no, that is VGS. Just check. VGS here. Okay. And this side we have GM, VGS, and RD. Draw that. This is GM, VGS. We have RD. And just check this RL connected between drain and VDD, that will be grounded during small signal analysis. Drain and VDD, it will be grounded. R. And we are taking output voltage across RL, that is V0. So the model is exactly same. The process is exactly same. And this current is IT. And this current is IL. Okay. So this is the small signal model, and using this model, we have to calculate other parameters such as the voltage gain and output resistance. So can you tell me how this IL and this small ID, they are related? Anyone?
ID equals to minus IL.
So minus IL. So what will be the value of V0? Output voltage V0. Because we are going to calculate gain V0 by Vi. What will be the value of V0 in terms of I and R? Okay. So we are going to derive the voltage gain. AV, that is equal to V0 by Vi. Okay. So V0, that is equal to IL into RL. Okay. Now IL, that is equal to minus ID. So we can write it is equal to minus of ID into R. Okay, very good. Minus of ID into R. Now actually what is ID? Just take a look. We know the formula of ID. Just check. We have ID equal to this for equation you put Gm VGS plus VDS by RT. Like that. Gm VGS plus VDS by RT. This is the value of ID. Okay, ID we got from the equation. Now in this circuit, if you compare, okay, this circuit and this circuit, what is the value of VDS? Check carefully. Here it is VDS. In our circuit, it's something different. So what is the value of VDS in our circuit? VDS means the voltage between drain and source. What is the value of VDS? Anyone?
RL.
That is V0. Okay. So VDS and V0, they are same. Check. Here it was VDS. Now in our case, it is V0. So, and so here we can write VDS equal to V0. What about VGS? Check. Can we say VGS equal to V in VI? The voltage
Yes,
between
sir.
this point and this point, it is exactly same because it is open. Okay, so VGS equal to VI. Just put that. So ID equal to GMVI plus V0 by RD. Okay, this is the value of ID. Now put the ID value here. So V0 equal to minus ID into RL, that is minus GM VI RL plus V0 by RD, okay, into RL. Okay, so just multiply RL and put one minus because it is minus ID into RL. Okay, yeah, I'm putting the value of ID here. This. So then our target is to calculate this. Just take some common and do it. What will be the value of AV? That's simple. Because see, left side we have V0, right side we have something V0. Okay. This one we have Vi, so we have to calculate V0 by Vi. That is again. So calculate it. So AV, that is equal to V0 by Vi. If I take common V0 common, can you tell me what is the value I'm getting?
Minus GMVI divided by 1 plus
No, I want to calculate V0 by Vi.
minus GMRL
Yes,
divided by 1 plus RL by RT.
this one. Minus GMRL by 1 plus RL by RD. So all of you are getting this. Okay, again I am rewriting this here. So AV equal to minus GM into RL by 1 plus RL by RT. So we can write this in this way. Just I am simplifying the denominator term. Minus GM into RT into RL by RD plus RL. Just I am simplifying this one. Okay. Now take a look of this factor, this one. What is that? RD into GM, that is equal to amplification factor mu. Okay, let's check. GM into RD, so that is equal to amplification factor mu. So we can write it in this way. The gain AV, that is equal to minus mu RL by RD plus RL, where mu equal to RD into GM. That's all. So this is the expression for voltage gain of a common source amplifier. Okay. Now, if I want to calculate the second part, that is output. Okay. So output resistance calculation. Output resistance calculation. Okay. So how to calculate this? So again, draw the model. So here we have VI. This one is the VGS. This side we have GM VGS. This side we have RD. And here we have RL. Okay, this is. Now for output resistance calculation, so we have to follow some steps. There are different techniques to calculate output resistance. Anyways, the most simplified, the basic fundamental for technique I am following. So VI will be 0, RL will be infinite. We have to follow this. Source will be 0, load will be infinite. Okay. Then, okay, let's follow. If I put VI 0, so when VI equal to 0, what will be the value of VGS? Just see the circuit.
0.
0. Very simple, because VI 0 means VGS 0. So what will be the value of GM VGS?
0.
0. The value of current source 0 means what? Short circuit or open circuit?
Open circuit.
Open circuit. Good. So GM VGS 0 means it's a current source. It's value 0 means it's open circuit. Voltage 0 means short circuit. Current 0 means open circuit. So let us see what we are doing actually. So it is open circuit. Okay. So by putting VI equal to 0, we got several approximation here, several simplification. Got this. The circuit looks like this. RL equal to infinite means RL open. Open the RL means remove the RL. Open RL means indirectly I am telling remove the RL. There should not be any load. Okay, open the RL. Now, if you see from this point, what is the value of impedance, or what is the value of impedance you are seeing from the output terminal between this and this?
RD.
That's all. So R0, that is equal to RD. That's all. Okay, the output resistance of common source amplifier. Now in the next step, let us solve another one. The second configuration, it is also common source amplifier, but with a little bit modified version.
सर
It
थोड़ा
is
पहले वाला स्लाइड देखने.
this one.
No sir.
It's
सर वो जो मतलब आउटपुट रेजिस्टेंस कैलकुलेशन.
this one.
Yes.
So VI 0, because it's the condition. Whenever you are going to calculate output resistance for any circuit, not only FET, for any circuit, always the input, whatever the input you are applying, that will be 0. Means if it is voltage, it will be short circuit. If it is current, it will be open circuit. And second thing, you have to open the load, disconnect the load, RL equal to infinite. Okay. So now in my circuit, when VI 0, of course VGS will be 0. So value of the current source, which was here, GM VGS, it will be 0. So it's open circuit. Okay, just remove that. So now only one element is present in the circuit, that is RD. So the output resistance means it is related to output. So if we see the resistance from this terminal, we can place only one resistance, that value is RD. So RD is the output resistance, RG. So R0, that is RD in this case.